Okay, let's come back to lesson 3, the quantum numbers. The quantum numbers have the principal quantum number. Principal quantum number have the K shell, L shell, L shell, and N shell. For K, N equals to 1, L, N equals to 2. For N equals to 3. For N equals to 4. But the number of electrons in a subshell is given by, or in a shell, sorry, given by 2n squared. So we're going to calculate the number of electrons in each of the shell. So using the formula expert, so make use of the formula here. 2, 1 squared, so in this case are 2 effects. Here is 2 into 2 squared. So that 2 squared is 4 times 2 is 8. 8 electrons. You have 2 into 3 squared. So that 3 squared 9 times 2, 18 electrons. 18 electrons. You have 2 into 4 squared. 4 squared, which is 16 times 2, or 32 electrons. Now 32 electrons. In conclusion, the K shell take a total of 2 electrons. So we can write like this: K2, K, L8, M18, M32. So where N is the principal quantum number. So our configuration at the ordinary level is usually written as 2:8:2. But advancedly, we're going to use the subshell. Talking about subshell, we're going to see the azimuthal quantum number. The azimuthal quantum number. Azimuthal quantum number. Azimuthal quantum number is common azimuthal quantum number. Azimuthal quantum number. For the azimuthal quantum number, it indicates a subshell in which the electron is found. So, the azimuthal quantum number starts called L equals to 0. N. So for L equals to 0, we have the S subshell. For L equals to 1, we have the P subshell. L equals to 2, we have a D subshell. L equals to 3, with F subshell. Hence, the SPDF configuration. Then, these electrons inside the subshell have orientation. They are being oriented. This orientation is determined by the magnetic quantum number. The magnetic quantum number is common 3 over 3. The magnetic quantum number. The magnetic quantum number. So the magnetic quantum number is given by M. M is equals to plus L2 minus L. So the magnetic quantum number depends on the azimuthal quantum number. So it doesn't have a range of numbers. That range is from plus L to minus L. Example, if L equals to 0, M is 0. If L equals to 1, M will be minus 1. 0, 1. So the M0 means that it's just having one quantum case. But here there are three numbers, the three magnetic numbers. That means there are three quantum cases. Here we can write 3.0. For L equals to 2, M will be equals to -2, -1, 0, 1, 2. In this case, there are up to how many numbers? Let's connect these numbers. 1, 2, 3, 4, 5. There will be 5 quantum cases. 5 quantum cases. For N equals to 3, N equals to 3, M will be -3, -2, -1, 0, 1, 2, 3. So let's count the number of numbers. The number of numbers you have 1, 2, 3, 4, 5, 6, 7. That means there are 7 quantum cases. 7 quantum. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. There are 7 quantum cases. So on the board we have the azimuthal quantum number, which indicates subshell in which electrons span, or the magnetic quantum number. The magnetic quantum number is the orientation, the position. Even though for the Heisenberg law of uncertainty, it's impossible to know the exact position of an electron and atom, but we can have a wave function. The wave function can give us a probability function where the electron might be found, or a region with the highest probability of finding an electron. That's why we call it an orbital. So an orbital is a region in an atom where there's the highest probability of finding an electron. This region, there are quantum cases. That's what we call the first quantum case is when N is 0. The magnetic quantum number N is 0, because N is plus N to -10. So for N equals to 1, the N is -1, 0, 1. For N equals to 2, N is -1, 0, 1. In this case, it shows that there are 5 quantum cases. 1, 2, 4, 5. For N equals to 2. For N equals to 3, there are 7 quantum cases. That is why here, for N is 0, we have the S. Here we have the P. Here we have the D. And here we have the F. Each quantum case carries a total of 2 electrons. It means that the S orbital takes a total of 2 electrons. 2 electrons. The P subshell take a total of 6. The L, the D take a total of 10. The F take a total of 14. Why? Because each quantum case takes a total of 2 electrons. But for M is 0, only S subshell, F subshell will carry those 2 electrons. Then if here, there are 3 boxes and each box carries 2 electrons. So that is 2 times 3, which is 6. For the D subshell, there are 5 boxes and each box carries a total of 2 electrons. That is 2 times 5, 10 electrons. For N equals to 3, which is the F subshell, there are 7 boxes that each box carries a total of 2 electrons. That is 2 times 7, which is 14 electrons. And lastly, we are going to see the spin quantum number. A spin quantum number. A spin quantum. The spin quantum number. An electron in a quantum case have 2 possible spins. That is the up spin The up spin is represented like this, and the down spin is represented like this. The up spin is plus half, the down spin is minus half. So it's that plus half minus half cancel. So it's impossible to have two electrons having the same spin. That's why impossible from the Boole's law. What is the physical significance of that? We here have the up spin. Here we have the down spin. Let's say if we have two electrons in the quantum case, the electrons are represented like this. One electron is pointing up, the other electron is pointing down. So that we have two pairs. That's the up spin and the down spin. The up spin and the down spin cancel up. What if we cancel two again? It's impossible to have electrons having the same spin, yet it's impossible. Also, the relatives of impossibility, having similar scale, impossible. So, either the electrons and the electron is in the up spin, the down spin, up and down. Up, no, cannot do. If it's up, we're going to see that we have plus half times plus half. The plus charges are similar charges, so they repel each other. Or we have the down speed. Down speed is minus half. But minus and minus half, they will repel because light charges repel. But the correct orientation of electrons is one electron is up speed, the other electron is down speed. So those are the various quantum numbers of an electron in an atom. So our next today will be the electronic configuration. So the electronic configuration in this case will be given using the SPZM rotation. So the SPZM rotation is nothing respecting some rules. The first rule we're going to see the Aufbau rule. So the Aufbau rule, we're going to follow the Aufbau for the electronic configuration. So let's for electronic configuration. Electronic configuration. So the electronic configuration is given using some rules. We are going to follow some rules. Rule 1 is the Aufbau. So 1s, 2s, 3s, 4s, 2p, 3p, 4p, 3z, 4z. Okay. So whenever you want to write the electronic configuration of an element, you are going to put the electron like this. These electrons, with the feeding of these electrons in the subshells, follow a rule. So follow the arrow while feeding the electrons. So let's take an example of an element. Let's take the element of calcium. When while filling this electron, you need to keep in mind that the S cup shell take a total of 2 electrons. The P take a total of 6. The D take a total of 10. The F take a total of 4. So writing the electronic configuration imposes 1. Calcium plates. 1s, we can follow the arrows. 1s2, we call it S orbital in total 2 electrons. So whenever you see S, you put 2 electrons inside. I have 2s. So after 2s, I follow the arrows. 2p, 6, 3s, 2. They will count a number of electrons. Here's already 10, 12. So 8 electrons stay. So we're gonna be 3p. 3p6. 4s. If it's so let's count the number of electrons and see. Let's upgrade 10 plus 33. So that's the electronic configuration of gas. So if I take another element of our choice, in this case, from the electronic configuration, you can rotate the element on the periodic table. So let's locate this element. The highest quantum number is 4. So it means the element is falling in the period 4. The period is 4. Then I have to know the group to which the element belongs. The group for an S block element, the group represents the number of electrons in the outermost shell. Or the outermost shell. The number of electrons that 2 of them are going to say group 2. The group is written in the Roman numeral, while the period is written in Arabic numeral. So we're going to take another element like the case of. So let's take the case of silicon. Silicon is 14. So let's give the quantum cases. Here we feel we have voltage. We have 1s2. We have 2s2, 2p, 6, 3s. Yes, already written. I mean, there is 10 plus 12, 3p, 82. There's a difference between the two type elements. The first element was an S block element. An S block element is an element whose last valence electron enters the S subshell. So here's an S block element, but here now a P block element. A P block element is an element whose last valence electron enters the P subshell. In this case, the period is the highest quantum number. The highest number is because I'm having 1, we have 2, we have 3. The highest quantum number in this case is 3. So here is the look at I click me. So the element is one period. Here click. But now the group will have a small problem with the group. The group now we should not just read at the last valence electron, if not the wrong. But here, given like was an S block element, for an S block element, you will read the normal connection in the uppermost shell. But for a P block element, the configuration of P block element is endless. MP. So we're going to add the S and P electrons. So that 2 plus 2 is 4. So in this case, I went out with 4. So here we have group 2 because it's an S block element and 2 electrons that are machine. Here's the P block element. The configuration finish P. That is why you add the P and the S electrons. So the element is found for purity. So this is one way of writing the electronic configuration of an element. We can write also the electronic configuration using the electron in box configuration. Such configuration is usually used for representing the elements of the transition metal, the configuration of the element with transition metals, or the D block element. So let's see how we can represent the electron in box or the configuration of an element using the electron in box configuration. Electron in box configuration. Electron in box configuration. So let's take the case of ion. So I want to write the configuration for ion. Ion atomic number is 26. So to write such electronic operation, we use the argon curve. So using the argon curve, we use argon. So put argon 3D or S. Remember that by filling these quantum cases or filling the subshell, we first of all fill the S orbital before filling the D. Argon atomic number for argon is 18 plus 2 as kids. So like 18 plus 2 that's 20. Out of 26, we'll write the 6 electrons. So 6. So this is the normal configuration of the element. Then now I'm going to use the electron in box configuration. So in the electron in box, we have argon. Remember that the d orbital take a total of a d orbital at that fine boxes. So okay, that fine boxes. So yeah, really see. Yeah, but correct. Kuhn's law. Kuhn's law is saying that why filling these quantum cases? You start by filling 1 1. That means you give 1 electrons each on the quantum case until everybody has 1 before you start doubling. That's what Kuhn's law is saying. So let's say Kuhn's law. I fill the electron 1 1 2 3 4 5. I hear that all the quantum cases have 1 electron. So I start doubling now. So I double. Again, I will just put 1. So it has me 1 already. I start double. You say I expect the spin, the Pauli exclusion principle. The Pauli exclusion principle tells us that the electrons should not have the same orientation. So if you are having the up spin, the other one has the down spin. So in a nutshell, that is how we present the electronic configuration of an element using the electron in box configuration. So you start, you respect Kuhn's law and the Pauli exclusion principle. What's the physical significance of that? We fill the electrons. You give 1 electron to everybody, or all the quantum cases, until all of them have 1 electron. That is start doubling. Also, electrons should not have the same spin. That is, if 1 electron have the up spin, the other one has the down spin. So we arrive at the end of our lesson of today. That was actually, or the chapter today, that was the atomic structure. Under the atomic structure, we saw 4 main points or lessons: the subatomic particle, radioactivity, the quantum numbers, electronic configuration. So thanks for watching and follow more on EduQs.